Good afternoon. My capstone project is the management plan for medical diagnosis chatbot. Our goal is to use machine learning to provide accurate preliminary triage recommendations to users reporting symptoms, ultimately improving resource allocation and patient safety in a high-volume clinical setting. This presentation outlines the strategic and architectural decisions required for successful deployment. We assess this opportunity using the three model criteria. 1, business value. The current manual triage process is slow and inconsistent, leading to unnecessary urgent care visits. Our chatbot will automate and standardize initial triage, reducing operational cost and patient wait times. 2 is the machine learning feasibility. This would be considered a hard problem. It requires complex multi-class classification based on the combinations of symptoms, which is a core strength of machine learning that's supervised, unlike simple rule-based symptoms. And then data availability. We have access to historical patient records containing symptoms and confirmed final diagnoses, providing the necessary labeled data to train the model. According to the CRISP DM model, success must be quantified, so our outcome metric is the business impact. We would say a 15% reduction in non-emergent patient overflow to the emergency room would be a success, as measured 3 months post-deployment. The model's technical success or output metric will be evaluated using the macro F1 score, which must exceed that 0.85 on the held out test set to ensure high precision and recall across all major diagnosis classes. The relevant factors here are patient demographics, reported symptoms, and their medical history. Our solution concept is a supervised multi-class classifier, likely using a transformer or gradient boosted tree to map a user's symptom vector to a triage category, for example, self-care, primary care, or emergency care. The data is comprised of structured feature inputs, such as patient vitals, pre-existing conditions, and unstructured text inputs, where they would put in their symptom descriptions, which requires natural language processing for feature extraction. Validation of the concept is crucial before production. We will follow an extensive plan. Phase 1 is our testing or shadow testing. The model will run silently on historical data to confirm that 0.85 F1 target score. Phase 2 will be live testing, where we will deploy the chatbot to a small controlled group of users. For every diagnosis the chatbot gives, a human clinician will independently review and log their recommended triage. We will use this human feedback as the ground truth for improvement. This ensures safety and builds clinical or clinician trust. Focusing on Model 4's system design decisions, we chose a batch training system. The architecture is defined by 5 key strategies, first being data ingestion and validation from the electronic health record system, then feature engineering, where natural language transforms unstructured text into embedding features, then model training using our selected algorithm, and then evaluation, where performance is measured against the F1 score target, and then finally model registry, which stores the successful model artifact with full versioning and metadata ready for deployment. This structured approach ensures reproducibility, and we can audit it, which is paramount in a medical system. Our primary focus for machine learning operations is mitigating concept drift and data drift. Concept drift is the most dangerous. If a new disease variant emerges or if diagnostic standards change, the relationship the model learned becomes obsolete. We would mitigate this by monitoring our output metrics weekly, triggering intermediate human review and potential retraining if performance drops significantly. Data drift occurs if the demographics of our user base change. So a new geographic region, for example, we will mitigate this by continuously monitoring the input feature distributions like age and reported symptom frequency, and then triggering retaining on a newly representative data set if required. This plan ensures we move beyond a successful experiment to a successful product. Our next step is to secure the necessary engineering resources to build the end-to-end pipeline. Thank you very much.